So the recording is going, and picking up from where we left off last time, we were almost done with chapter 3. Not quite. So I introduced all the relevant ideas, or the relevant objects, namely divergence and curl, and again, no justifications given because it's premature. We need to develop a bunch of stuff in chapters 5 and 6 first before we can really begin to make sense out of what are actually really chapter 7 concepts. So, but anyway, we introduced them a little early so you have time to kind of get used to the idea that we're going to apply operators to vector fields and that they're going to have these geometric interpretations. So the last thing I want to throw in there, and this is supplemental to the book, and I think this is really useful, not to mention culturally valuable. Sort of, there's certain things that I think it's good to be aware of about what the future of math, your math experience, math classes that you haven't taken yet and might in fact never take. Still, it's good to know approximately what the story is. So it turns out that it makes great sense to compose these 3 operators in this order. Now, why is that? Long story. And well beyond what we can comfortably do in this course. So I'm not going to tell you all that stuff, but it turns out this actually makes great sense. Composing them specifically in this order. Gradient first, feeding into curl next, feeding into divergence last. That specific order. So first thing I'm going to tell you about this is what we call an exact sequence. And I do have to, qualifier. There are some regularity points that need to be made, and we do have to worry about constant functions in here. Turns out that they're a different story. And so, a couple of disclaimers and exceptions granted. But that said, roughly speaking, this is an exact sequence, and what I mean by that is all the lifetimes are 2. Now, what do I mean by a lifetime? Here's an example of a lifetime. If I have a function to which I apply the gradient, which of course then gives me a vector field, and then I could talk about taking the curl of that, and let's suppose, hypothetically, that I got 0. Let's just say. Right? A plausible story, one could imagine. This is what I would call a lifetime of 2, in the sense that, I like to think of 0 as kind of being death, in a way, if you will. It's a metaphor, right? Don't take this too seriously, but nothingness, if you will, right? I don't want to get philosophical or religious here, but furthermore, no matter what you do to 0, guarantee it's going to stay 0. Again, the analogy kind of works, right? So anyway, I think of 0 as being kind of like death. And you could think of this as kind of like birth because, well, there was nothing that came before it. Right? So in my little metaphor, we have birth, survival, and death. And the lifetime length here is 2. Oh, thank you. I was hoping someone would do that. Lifetime of 2 because there were 2 steps in this little story here. Okay, so that's what we mean by a lifetime of 2. Now it could be that I have a vector field that I take the curl of to get, of course, another vector field, and that maybe I take the divergence of it and get 0. This also is a lifetime of 2, but where this is useful is you might wonder to yourself, hey, couldn't it be that this initial vector field itself might be the gradient of some function? And if that were the case, wouldn't that mean that the total lifetime was 3? Right? Well, so the rule here that all lifetimes are 2 is what makes that not possible. All lifetimes are 2 means you can't have this be where this story begins. This can't be where it was born, because if so, then it survived to here, and then it survived to here, only to die there. That would be a lifetime of 3. Not allowed. The lifetime is 2. All right. So you can consider various different versions of this. Here's another one. If you have a vector field and you take the divergence and you get 0, lifetime is 2. That means that there must be a vector field whose curl is your original vector field. Or said differently, your original vector field, your vector field whose divergence was 0, has an anti-curl, you might call it. And that's the term I like. Again, not popular. I'm trying to popularize it. Okay, so there are, again, lots of different versions. You can write this down. I mean, again, so the curl of a gradient, always 0. That represents a lifetime of 2. So any gradient, whatever it's a gradient of, curl is 0. As one of the examples I already talked through, if the divergence is 0, then that vector field whose divergence is 0 is a curl of something else. So I like the metaphor, because without the metaphor, there's like 8 different statements to be memorized. And it'd be easy to forget one. It'd be easy to kind of get them backwards, to inadvertently, not thinking about this diagram, to think, oh, wait a minute, is it the divergence of the gradient that's always 0? Oh, which way does it go? You get it wrong, right? Easy to sort of get things confused around. But remembering that the composition is in this order, and remembering that all lifetimes are 2, pretty much does it. Okay. All right. Now, the last thing I'm going to say is that, as you might sort of kind of be picking up from this little story, I mean, how mysterious is it that we compose them in this order for reasons that I have not given you any reason to believe particularly? And what's the deal with the lifetimes? Doesn't this seem mysterious? Doesn't it seem like there's got to be reasons to all this? And doesn't that make you wonder, mightn't there be more connections, more relationships between these operators? And the answer is, oh yeah, absolutely. There is a lot more going on about how these operators relate to each other and connect to each other in different ways. And that's going to be pretty much what we're going to talk about for these 2 chapters. So anyway, again, just a little bit of foreshadowing. Wanted to let y'all know what to keep your eyes out for. And with that said, we're moving on now to Chapter 5. Okay. Now, you may have noticed, we skipped Chapter 4. Where did Chapter 4 go? We are going to cover Chapter 4. You'll notice it is on the content syllabus for the course. We are temporarily skipping it due to a combination of circumstances as follows. Chapters 6 and 7 are the most... I'm going to say they're the hardest part of the course. They're also the most interesting part of the course. But those are the chapters that have the most ideas in them. Those are the ones that you're going to need the most time to digest and absorb and you get comfortable with. And yet they come at the end of the content syllabus, and I don't want it to be the case that you learn that material right at the very end of the course, and then the final exam's 4 days later. Right? That's no good. This is suboptimal, highly suboptimal. So anything I can do to push chapters 6 and 7 earlier into the term is a good thing. Of course, if I move chapters 6 and 7 earlier into the term, something has got to go back to the end of the course. And of course, I can't do that unless the material isn't prerequisite. I can't move prerequisite material to after chapter 6 and 7. Well, it turns out chapter 4 is pretty much the only non-prerequisite material. So I'm delaying chapter 4 just because we can, and because that'll make chapter 6 and 7 go better. Okay. So that said, here we go, chapter 5. We're going to talk about integrals. And I'm going to start off with a convenient lead-in. Oh, by the way, I discovered a typo here. No one's noticed this before, but partial derivatives are in chapter 2. Sorry about that, not 3. So I need to fix that in my notes. Feel free to scratch that out and just write 2 on top of the 3. I don't brain spasm. Anyway, the way I presented partial derivatives, you may recall, I started chapter 2 with partial derivatives. But I gave you this disclaimer of, look, they're good for a lot of things. I'm for partial derivatives, but that's really not the fundamental point of view that you should have on multivariable derivatives. Multivariable derivatives are best understood by way of the derivative matrix, right? It's the relationship between input changes and output changes. It's really the more natural and powerful way to think about multivariable derivatives. Okay, so same deal here. I'm going to start off with something that's convenient, and it's nice in certain ways. It's going to answer certain questions for us. It's going to be familiar. It's going to look a lot like single variable integrals. All this is good, but please do not hang your hat on this. Do not set this as the cornerstone of your point of view on multivariable integration, because I don't think this is the right point of view. It's importantly not the right point of view. But it's nice to start with something familiar, get one into the win column, and we'll come back and do something better in a little while. Later today, actually. Okay. Flashbacks to Calc 1. Oh, probably Calc 2. Calc 2. Right? If you have a rotated surface, like this surface here, and you want to compute the volume that's on the inside of that surface, y'all have all seen these kinds of questions. And the big idea is that you understand the volume by slicing it into little slices of volume that look kind of like this, right? And then understanding the slices as much simpler questions. For example, this slice here, forgive me for a second while I try to draw this, but this slice here is this area times whatever the thickness is. Right? So cross-sectional area times thickness gives me that little piece of volume dV. Look familiar? Cool. So, nice. And this is something I can compute, but do notice that in order to be able to make any sense out of this, I do need to be able to compute that cross-sectional area. In this case, I can compute this cross-sectional area because it's a disk. It's a garden variety, standard, boring geometric figure whose area formula y'all have known since probably middle school. Okay, so that was lucky that the cross-section was easy. All right, now that in mind, let's try to take the same approach to a different question. Instead of rotating a single variable graph, how about I just look at a multivariable graph, such as this one here. Notice this is a graph of a multivariable function. So it's a surface, and I can ask, very reasonably, how would I compute this volume? Specifically, volume sitting over a certain rectangle. We're going to look at this rectangle right here, arbitrarily in the XY plane. And so, again, it's a volume. Again, I've got equations describing the parameters of the question. And again, with the above in mind, with this strategy in mind, how about I just take slices and hope that it works out? So I'm going to, same deal, I'm going to take slices such as this, right? And can I, copying from up here, can I understand the volume of, not that slice, but now the volume of this slice as being a cross-sectional area times the thickness? Well, the problem is that this cross-sectional area, give me a second again, I like to draw these things, this cross-sectional area here, this is not barnyard variety geometric figure. right? It's not a disc, it's not a triangle, it's not a rectangle. It's weird. And I don't have any barnyard variety formulas that I can just cite that tell me this area. And so there is a temptation to say that we're dead in the water. Everybody see the problem? Here's the move. Correct, it's not a barnyard variety geometric shape. However, it is arguably a shape that I have some experience with computing the area of. After all, this area is the area under a curve. Right? There's that curve right there, and I know how to find the area under a curve. Well, specifically, I know how to compute the area under a graph. Right? Well, golly, this kind of is a graph. It's certainly part of a graph. The graph is a surface. This is just a curve. But it's like cross-section of a graph. Maybe that's enough. And it turns out that it is. So here's how we do it. Looking at the next page here, again, I have this curve. I claim that this is literally a graph of a function. It's the graph as follows. Now, a couple of little details we have to keep track of. Notice, in order to compute this cross-sectional area, let's see, area in yellow. In order to compute this cross-sectional area, I have to be clear about for what value of y. You know, where in my slicing process, right? I'm slicing up perpendicular to the y-axis in this case. Where in this slicing process am I? What is the value of y that defines this slice whose area I want to even talk about? If y isn't fixed, there is no slice, there is no question to answer. So keep in mind, in this situation, for the purposes of computing this area, that y there is fixed. It's constant. So how about that? Now let's think about what is x doing. X is actually a variable because x is going to go from A to B, thus causing this combination, this ordered pair x comma y, to go right across there, right directly under this curve, the area under which I want to know. Right? So I can talk about these sort of base points down here as well as just x comma y with the understanding y is fixed. Everybody with me? Okay. So this is a single variable function, and furthermore, the heights here are z. After all, that's what we do with the function when we're talking about a graph. Right? So this function, this single variable function, f of x comma y, with the understanding that x goes from A to B and that y remains constant, this is exactly, precisely the function whose graph is my curve that I want to compute the area under. And how do you compute the area under a graph? Well, integral. I just let x go from A to B, integral dx, boom, area. Everybody with me? What do you think? Questions? Everybody happy? Okay. Sweet. Well, it's all over for the shouting. For this calculation anyway. So I got my formula here for the area. The area is that. Don't forget that area times thickness is what gives me volume. The thickness here is going to be sort of a thickness along the y-axis. That thickness then is going to be dy. Area times thickness will give me the volume of the slice that I need. And so this little, where I was out of luck on the previous page, trying to find this volume of this slice here. No longer out of luck. Volume of that slice I now have a perfectly reasonable formula for, and there it is. And just like on the previous page, that volume I just have to add that up over all possible values of, all possible values of y. So I've got to write this down for as y goes from C to D. So y goes from C to D, and we've got ourselves a formula. What do you think? Everybody okay? Okay. So that's the big idea. This is called an iterated integral. The idea is because it's an integral of an integral, and so you can just kind of see the etymology there. That we're doing an integral and then we're doing another integral, and when you repeat an operation, that's iterating that operation. It's the motivation for that term. My quibble, and this is a annoyance for me, but that's just me being grumpy, is that we're not actually doing the same thing twice. We're doing two different things. We're doing an x integral followed by a y integral. They are different things. I'm not really repeating the same process twice. So that said, I don't really prefer this term. I like the term nested integral because it truly is an integral sitting inside of another integral. Right? So that's commonly called a nested expression, or dolls inside of the larger doll boxes inside of larger boxes, whatever. So this has not caught on as I've been hoping. We'll see. Time's not up yet, but the common term, the term that we should use in this class because it is overwhelmingly the most common, is iterated integral. Is everybody on board? Okay. Alrighty. A couple of things before we actually crank one out. Let me observe an issue with terminology. When I developed this expression, when I developed this iterated integral, recall the very first thing I did is I said we're going to do a y integral. We're going to think about what happens as y goes from C to D, and then we started worrying about cross-sectional areas, and the cross-sectional areas gave me an integral dx from A to B. So that said, the dy integral was written first. Wrote that down as we were developing this iterated integral. The dy integral came first. But now let's think about how we evaluate. How would I evaluate this integral? Can I start by evaluating the dy integral? I don't know. I can't, because the integrand I don't even know yet. I don't know what that integrand formula is because I haven't evaluated my dx integral yet. Right? So when it comes to evaluations, you kind of have to do the dx integral first. So this is a terminological problem. If I say the first integral, do you mean the one that was developed first? Or do you mean the one that's going to be evaluated first? The term is unclear. Right, so this is not good. We don't want to use unclear terminology. So I think this idea of a first versus second should be avoided, and rather instead you should use, I think, much more clear terms inside. The dx here is clearly on the inside versus outside. The dy integral in this case clearly on the outside. How are we doing? That makes sense? So you're going to hear me talking about the inside integral, the outside integral, the inside variable, the outside variable, stuff like that. Okay. Alrighty. Next thing, keep in mind, while you are doing the inside integral, so for the purposes of computing what we have here, now before I finish that sentence, let me remind you, what was this thing on the inside? Its whole job is to compute this cross-sectional area. And for that cross-sectional area, I need to know what single value of y are we talking about. In other words, don't forget that y is fixed. Y has to be constant for the purposes of that inside integral to even make sense. So don't forget, saying that y is constant, notice that y is the outside variable. So the easy way that you can remember this is that however you do your cross sections, whichever order you do it, you can switch the order, by the way. We'll talk about that in a moment. It's always the case that for the inside integral, the outside variable must be treated as a constant. Anybody on board? Okay. All right, now let's do one. Alrighty, so here we go. Volume under a graph. Whoops. Highlight better. Volume under a graph. Want to compute this volume here. Specifically, this graph of that function, which is a paraboloid, and a little bit of an art challenge there, by the way, to think how would you draw just the part of this paraboloid graph that sits over this oddball little rectangle over here off to the side. I'm trying to draw just part of a paraboloid. I hope this is suggestive of that. Okay, before I get into the computation, a little notation. This looks kind of like a cross product. It's not. This is just a different use for the times symbol. This is a reference to a rectangle as follows. Whatever the interval is on the left tells you the range of values for the first variable x. Whatever interval is on the right is telling you the range of values of the second variable, in this case y. Then saying times is just code for we want to talk about the rectangle in the xy plane where x ranges over these values and y ranges over those values, and that gives us this picture right here. Is everybody okay with that? It's very convenient notation. We're going to use this a lot, so be on the lookout for it. Okay. So, getting into the answer. We've already argued that the volume is this iterated integral. We don't have to reproduce that argument. The argument's already been made. Yeah, go ahead.
Does it matter if the 0 and the 1 go on the outside of
it? It does, yes, correct. So this range of values here, that's the range of values for x specifically, and so it has to be the bounds for the x integral. Okay. Yeah, absolutely. Does that make sense? Everybody else good with that? All right. Good. Okay. So, here we go. Let's start computing. Keep in mind, for computational purposes, I've got to start on the inside. I can't do the dy integral yet. I don't know the integrand for the dy integral. So we start with the dx, and we start with the inside integral. Also keep in mind, while we're doing that inside integral, the outside variable is constant. So y, as I'm doing this inside integral, y is constant. That means that y squared is a constant. And here's what messes up a lot of students. A lot of students they'll see the y squared and they'll think, oh, I'm doing an antiderivative. And the antiderivative, see power rule and all that. A lot of students will think 1/3 y cubed. And it's not. Because y is not a variable. Y is a constant for the purposes of this inside integral. And so I treat it as a constant. If you want to take the antiderivative of a constant, the answer is that constant times your variable. For the inside integral, the variable is x, so I get x times y squared. Everybody okay with that? A little bit of a landmine, right? It's easy to look at y squared and think about power rule and stuff. So heads up. That said, what about this x squared? Keeping in mind, for the inside integral, x is the variable. Oh, well, then I literally have the variable x squared. Taking the anti-partial with respect to x. And exactly as you would expect then, you get 1/3 x cubed. Is that cool? All right, here's the next opportunity for an oops. Now, as y'all know, the bounds are what you plug in for here. And here's a mistake that a lot of students will make. A lot of students will then say, okay, well, let's see, I've got to plug in, for example, I've got to plug in 1, so I'll plug in a 1 there, and then I'll plug in a 1 there, and then they kind of forget. They're busy plugging stuff in, and they forget that this expression, this factor right here, this y, is not the variable for this integral. It's constant, being as it is the variable for the outside integral. So some students will then also plug in the 1 in for y, and of course you should not do that. So my little hack for avoiding that kind of, obviously you wouldn't do it on purpose, but this little inadvertent thing is to whatever the variable is, note that specifically when you recopy these bounds. Don't just put 0 and 1 here and here. At some point, you're going to oversight, oops, and accidentally plug it in where it's not supposed to go. So, again, it only takes a fraction of a second to write x equals. So, grand total, a second and a half, right, to write down this extra thing. And it's an insurance policy that might save you, some significant points on the exam. So I think it's a second and a half well invested. Is everybody with me? Okay. So, alrighty. Well, you plug in x equals 1 into there, and this expression becomes that. And then you plug in x equals 0 into there, and this expression becomes that. And we have successfully computed our inside integral. Our inside integral is, it's this, it is this function of y. Now, this creeps out some students also sometimes. Wait a minute, I thought I computed that integral. How come there's variables still in there? This is an illusion. It looks like there's a variable still left in the answer, but there's not. Because y is the differential for the outside integral. Y is a constant. So as far as my integral is concerned, the one I just computed, as far as this inside integral is concerned, this is a constant. There are no variables left. So no problem. Everybody good? Said differently, what was the deal with this integral in the first place? Where did this integral come from? Well, that inside integral is the cross-sectional area, which should be a function of y, because depending on which value of y you pick, you get different cross-sections and therefore different cross-sectional areas. So it makes sense from multiple points of view that the result of the inside integral should be a function of the outside variable. Okay. All right. And then it's really all over at this point. I mean, this is literally straight up, no asterisk, single variable integral here, and antiderivative plug in, boom, answer. Yeah? Alrighty. Okay, now, I made a vague reference to, somebody asked me something about this. I made a vague reference to you can switch the order of the differentials, and here's that result. What we wrote down was that the volume could be computed as a y integral of the cross-sectional area, which itself was an x integral. And I'm going to leave this as an exercise for y'all. It's a really nice exercise. It's very doable. I think this would be a good learning opportunity. You can get the same volume by instead doing an x integral of the y integral. And the way you're going to show that is you're basically going to copy this entire argument here, except instead of taking cross-sections perpendicular to the y-axis and letting y go from C to D, you're just going to do it the other way. You're going to take cross-sections perpendicular to the x-axis. Think about how would you write a volume of a slice kind of like this. Area is now going to be a function of x, not y. So x will be a constant for the purposes of blah, 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 right? It's going to be very analogous. In fact, you can take the pictures and the algebra that I've got here and use that as a kind of a cheat guide, right? And just think in terms of how you would adapt appropriately. How does the diagram change? How does the algebra change? And what you will find is that this same volume that we previously computed with that iterated integral also perfectly fine as that iterated integral. All right, does everybody see what I want you to do? Nice little exercise. Again, if you have any questions, if you get stuck, not sure how to draw the picture, whatever the case may be, unclear about which role which variable is playing and which integral, no problem. Come talk to me in office hours, the other instructor's office hours, help room, what have you. Okay, one little disclaimer though. There's a hand-wavy representation of what's happening here. You have two integrals with bounds on the kind of the left side of these expressions, and then you have two differentials, with the variables on kind of the right side of these expressions. And this is what's going on, right? We're moving the inside to the outside and the outside to the inside. Notice the bounds come along for the ride, right? You switch the differentials, you also have to switch the bounds accordingly. But this only works if the domain is a rectangle. Things are going to be quite a bit weirder when we get into domains that are not rectangles, and we will do that. It's going to be pretty soon. It'll be on Friday, in fact. We'll get to it today. But when you have a rectangle, yes, you can just do this move right here. Is that all right? All right. Okay. So, now I have to present some bad news. Let me remind you that in single variable calculus, y'all have computed a bazillion things in single variable calculus classes. You computed area under a graph, sure, but you've also computed the mass of a rod, a one-dimensional rod. You computed the amount of work that it takes to perform a certain physical task. You computed the population of bacteria in a petri dish. You computed lots and lots of different things, lots of applications that single variable integrals address. Okay. Same kind of integral, by the way. So you might speculate, now that we've computed not the area under the graph, but the volume under a graph with an iterated integral, wouldn't you expect that we could make an analogous argument for computing all these other things? Like, instead of having a mass of a one-dimensional rod, what if I had a mass of a two-dimensional sheet? What if mass is distributed? Maybe I have literally a sheet of metal, and the alloy that makes it up is not constant. It's more iron on this side, and it's more aluminum on this other side, so the density varies. Well, in single variable, the same kind of integrals that compute volume compute mass. Now here in multivariable, wouldn't you think that the same kind of integrals to compute these volumes should also compute mass? Seems like a reasonable speculation. Let me show you why it doesn't work. Which is disappointing. Something very particular happened in this argument here. And keep in mind, I got to evaluate the inside integral first. I have to make sense out of this expression first. This is, in some sense, the very first thing that happens is this is a height. Let's see here. This is a height. This is a length. And the reason that I write down f of x dx is because height times length gives me area. And recall, we were looking at cross-sectional areas, and I was adding up little pieces of area like that. And so thankfully, knowing that this is area means I can draw pictures and make arguments. Okay. All right. Well, can I do that in this other circumstance? What is this? With now, instead, let's see here, this being density, namely mass per unit area. and this now again still being length, right? So I've got mass per unit area times length, and I asked the analogous question, well, what is this? What is mass per unit area times length? And, well, this is a mismatch, right? The whole idea of mass per unit area is that mass is distributed across an area so that if you have a little piece of area, you can take mass per unit area, multiply times that area, and the area cancels and you get mass. And then you're adding up little pieces of mass. Wouldn't that be nice? That's not what happened. Right? This expression, this iterated integral thing, forces me to make sense out of the idea of mass per unit area times length. And I don't know. I mean, I guess we could argue that maybe this is mass per unit width. Seems like maybe. Well, what is that? That's weird. Right? Think about population instead of mass. If we had population per unit area, that's a thing. I know what you mean if you say population per unit area. Got some piece of area. I don't know. Durham County, right? And there's a certain amount of population and a certain amount of area, and that's population per unit area. What would population per unit width mean in Durham County? I don't know. That's weird. Everybody see the problem? Okay. All right, so it just doesn't work. In some sense, the reason this one worked but this one doesn't is because we got lucky. There just happens to be this idea of area, cross-sectional area, coincidentally is a pre-existing thing that I can then take advantage of. And we just didn't get lucky here. Whatever this thing is, it's just not a pre-existing thing. Okay, so this is one of the big reasons that I'm a little bit, kind of sort of down on iterated integrals. Iterated integrals, as I've written them here, will connect directly, only to the volume question. That's kind of all they're good for in terms of, again, direct connections to applications. And that's not good enough. There's lots of other things we want to compute. I do want to be able to compute the mass of a rectangular sheet given a varying mass per unit area. We're going to need to be able to do that. I'm going to need to be able to compute populations given population per unit area. And I'm going to need to be able to compute, work and probability and a bunch of other things. Just won't do it. Okay. That's my gripe on that. Okay, so we're going to need a new construction. We're going to define something called a double integral. This is analogous to single variable integrals. In order for me to be able to talk about an analogy between single variable integrals and double integrals, in order to extend, in other words, that concept, I need to make sure everybody's on board with what a single variable integral is. So here you go. This is the definition of a single variable integral. An integral is a Riemann sum. All right, so I hope y'all remember this formula. A bunch of related expanding follow-up formulas to make clear what those objects are in the initial formula. So this is the working definition for the purposes of this course of an integral. I emphasize, though, a lot of students view this as sort of an alternative, and that, but you know what? Frankly, it's just much easier and better to think of integrals as being area under a graph, and this is a problem. Let me show you why. Here's a diagram representing the relevant objects. Various applications I want to find the answers to. I want to compute populations or work or mass, what have you. I can take all of these things, I can chop them up into little pieces, and I can make Riemann sums. Right? If I have a rod, one-dimensional rod, I want to compute the total mass. If I slice that up into little pieces, I can compute the mass of each individual little piece. Right? On each individual little piece, in other words, that's the mass of a little piece, density times size, and I can then add up over all of my pieces. Right? I can do that with any one of these. I can do this Riemann sum strategy for all those things. And then, of course, once I have a Riemann sum, aka an integral, I can compute with the fundamental theorem of calculus and game over, we win. Here's what you can't do. You can't make any sort of a reasonable, independent argument in which you claim that work is immediately understood as area. That just doesn't work. No pun intended. These are fundamentally different things. Work is a physics quantity. Area is a different thing, right? They don't have the same units. Why would work be an area? No direct connection. Okay. Now, what you can do, and a lot of high school calculus courses do, is kind of try to do this, but ultimately what they do is they say, well, yeah, but you imagine taking the work and kind of breaking up the little pieces, etc. They basically kind of almost rewrite it as a Riemann sum and then interpret the Riemann sum as an area. Yes, you can do that, but notice, in order for this to make any sense at all, you need the concept of a Riemann sum. So there's no getting around it. In order to make any connections at all, here, you must have this concept of a Riemann sum. Area is completely irrelevant to it. If you're computing the amount of, if you're computing a probability, given a probability density function, if you've done any calculus-based statistics, whatever, if you're computing work or mass or economic value, whatever, you gotta have a Riemann sum to make any sense out of it. And area, you don't need it all. I can rewrite mass as an integral. I can compute it. No area to be discussed. All right. Okay, so very importantly, integrals are Riemann sums. Integrals are Riemann sums by definition, as represented here. I'm going to stop myself from talking about that, but point out that for your reference, if you want to hear more about this, if your understanding of Riemann sums may be a little shaky, maybe your high school calculus teacher let you kind of blow off Riemann sums. We don't really need those anyway, and you're left maybe not with a good understanding of Riemann sums. On my miscellaneous topics playlist, I have a recording called "What is an Integral?" It's 30 minutes. Only about 10 or 15 of it is on this question of why do we need Riemann sums. And I think it's a really good discussion. I think it's a really important discussion. So if you want to hear more, there's your reference. And I hope y'all will take advantage of it. I'm also going to point out while I'm here, so little time left, trig substitutions. Very underappreciated trick, tool for computing single variable integrals. Lots of high school courses don't teach it. My experience as a second major in physics was that trig substitutions are invaluable in physics. And a lot of y'all are engineers, and engineers, not that different from physics, you're probably going to need to use a lot of trig substitutions. So maybe watch that one as well. Okay, so we are out of time, and we will pick up then here on Friday. Y'all have a good one. See you later. Don't forget to make me mark you down.